In the previous class, we were discussing Uni Junction Transistor. Okay, right? Why it is Uni Junction Transistor? Only one PN junction. Okay, we have seen this in the previous class, right? So only one PN junction, hence Uni Junction Transistor, right? Okay, so aluminum, right? To that you have the emitter terminal. This is N region. Two base terminals. Okay, base 2, base 1. This is the PN junction. So the equivalent is one PN junction, and then okay, a resistance, right? In fact, resistance between B2 and B1. Resistance between B2 and B1. Okay, right? But we are representing that by two resistors, one close to base terminal as RB2 and close to base terminal B1 as RB1. Okay, right? So this is the equivalent circuit for Uni Junction transistor. Further, we can represent this particular construction of the Uni Junction transistor in a somewhat different manner. Okay. Right. So we can represent the construction of Uni Junction transistor. Just a minute. Okay. So this particular Uni Junction transistor, we have a PN junction and then two resistances that we can symbolically represent as like this. A P region here, so we are writing a P region. Okay, then a P region here, so we are writing P region. Then the entire N region we are representing in the form of two resistances. Okay, what are the two resistances? RB2 and RB1. Okay, so the two resistances are RB2 and RB1. The same structure we are representing in a somewhat different manner. Okay, right? But what else we have? We have the electrodes emitter, base 2, base 1. So this one will be the emitter, base 2, base 1. Usually to the base 2, we connect positive of the supply. Okay, to base 2, we connect the positive of supply. Okay. So we will connect like this, positive of the supply to base 2. Obviously, the negative will connect to ground. Likewise, okay, to the emitter terminal, we will give positive on P side. Okay, we will give positive on P side. Obviously, the negative we will connect to ground. Okay, right? So what we are representing here, the UJT. Okay, right? What we are representing here, the UJT. We are representing in a somewhat different form, and also we are providing the voltages, right? Next, let us what we will do here is usually to get the UJT characteristics, what is done is this particular voltage, the output voltage is fixed constant. You gradually vary the input. Okay, plot the input voltage versus input current, right? So output is constant, input is variable. Variable we will represent with arrow. We have seen this in lab also, right? Variable supply we will represent with arrow. Next, let us name the supplies. This is VE because it is connected to the emitter terminal. Okay. So obviously the other supply will be VBB. Okay. The other supply will be VBB because it is connected between the two base terminals. Okay, right? And next what we will do is, let us mark the voltage at this point. Okay, let us mark the voltage at this point as some voltage VA. Okay, we will name it as some voltage VA. Right? So what we are doing? There is a PN junction. So we are putting P, right? The entire N region. P region here, remaining all N region. And the resistance of N region we are representing by two resistors. One close to base 2 as RB2, then close to base 1 as RB1. Okay, right? So PN junction diode, two resistors. PN junction is here. Okay, so right, you have PN junction, the junction is here, and that is connected to the junction of two resistances. The PN junction is here, that PN junction is connected to the two resistances, hence we have this structure. Okay. Next, what we will represent is, we will represent the electrodes, right? Okay. Usually, you don't directly take a wire and then connect to the electrodes. You have something called as metal contacts. Those metal contacts, let us represent like this. Then this one, okay. Then also at the bottom, right? Okay, so those are the metal. Any device has those metal contacts, right? Okay, so this is regarding the structure of the Uni Junction transistor. Okay, now what we will do is, we will understand how this particular device works. Okay, right? See, the way the syllabus is framed is, for one small PN junction diode, entire full unit. Okay, right? But whereas UJT, we have to give only two classes. That's the way the syllabus is framed, right? JNT has done it that way. There is nothing we can do. We have to conclude in two classes, but I recommend spend more time. Okay, watch the video again and again so that you learn this perfectly, right? Okay. Now, next what we will do is, we will try to understand how this particular device functions. Okay, so what I will do is, I will use two boards, right? So that we can easily compare these. Okay, so now what we will do is, we will first consider the case when the emitter current is 0. Okay, this is the emitter terminal VE. What happens when the emitter current is 0? We will take that case first. Okay, in such a case, okay, now emitter current is 0, right? Means as good as nothing is connected. Okay, nothing is connected to this particular P region. VE is unconnected. In such a situation, what happens? Okay, we are going to study now. So this is unconnected means it is as good as, okay, it is as good as the PN junction to the P side, nothing is connected. The terminal is open. So you have only one loop, VBB, RB2, RB1. Okay, right? So VBB is divided between the two resistances, RB2, RB1. So we can make use of voltage division rule and we can get VA. Can anybody use voltage division rule and tell me what is VA here for this case? What will VA be? VBB into, okay, RB2, sorry, VBB into RB1 by RB1 plus RB2. Okay, VA will be VBB into RB1 by RB1 plus RB2. So let me write that here. VA will be, okay, right? This one, VA will be RB1 into total voltage by sum of the two resistances. Okay, right? Voltage division rule. Using voltage division rule, we will get VA. Next, what we will do is let us, okay, let us consider that this ratio of resistances. Okay, we have the ratio of resistances. What is that? You have, okay, this particular RB1 by RB1 plus RB2. We have this ratio of resistances. Okay. Now, if you see the entire resistance between the base 2 and base 1 is simply nothing but RB2 plus RB1, right? Right. So VBB you can see here because it is connected between base 2 and base 1. Likewise, RBB will be RB2 plus RB1. Okay. RBB we can write it as RB1 plus RB2. Okay. Right. So RBB, the entire resistance between B2 and B1, we can represent it as RBB as RB1, okay, plus RB2, right? So how we can represent this? We can represent VA as RB1 by RBB, okay. This ratio of resistances is known as intrinsic standoff ratio. Okay, this ratio of resistances is known as intrinsic standoff ratio represented by eta. So, what is eta? Nothing but RB1 by RB1 plus RB2. So, VA we can write it as VA, we can write it as eta multiplied by VBB. Okay, we can write it as eta multiplied by VBB. Okay, so what is eta? Where eta is nothing but, right? Where eta is nothing but this ratio RB1 by RB1 plus RB2. Okay, but RB1 plus RB2 is nothing but RBB. So eta, you can represent it as RB1 by RBB. You can represent eta as RB1 by, okay, RBB. But remember, all this is for the case when IE is 0. Okay, we have started with IE is 0 when nothing is connected to the P side here. Okay, right? So you have to mention like this: when, okay, IE is 0. Okay, you have to mention eta is RB1 by RBB. Okay, when IE is 0, right? Okay. So this is we have, okay, this is what we have seen, right, so far. What is the voltage here? The voltage here, the expression we have obtained. Okay. Eta is intrinsic standoff, okay, ratio. Next, again here we will consider the case when this particular VE, the input voltage, is less than VA. Okay. So for what is VA, we have identified VA is nothing but RB1 into VB by RB1 plus RB2. Okay, right? Now what happens when VE is less than this particular VA, right? Now if you see the structure of, if you see the structure of, okay, it is better to understand from here. This is emitter voltage, this is VA, okay, this is VA, this is VE. So when VE is less than VA, voltage on P side is less than voltage on N side, okay, voltage on P side, voltage on P side is less than voltage on N side, VE less than VA. Then what happens? The diode is reverse biased. You know very well that when diode is reverse biased, the only current flowing through the diode is, okay, leakage current or reverse saturation current, right? So first, what happens when VE is 0? When VE is 0, because of this VVB connected on the output side, VA has some value, non-zero value. VA is non-zero and positive. VE is 0. Okay, we are starting the case. We are starting the case. Okay, we will plot the graph of current, okay, voltage versus current, and January 2020 fell on a Sunday. Okay, so we are going to plot the graph for, okay, current versus voltage. Now here you have to remember, see, for usually any of the graph we have seen so far, voltage you will take x-axis, current you will take y-axis. But for this particular UJT, we will take current along x-axis, voltage along y-axis. Okay, right? Now what happens when VE is 0? Okay, when VE is 0, then this particular PN junction is reverse biased, right? Okay, because VA is positive, VE is 0, so junction is reverse biased, some leakage current flows, okay, some leakage current flows, right? That we will, I am representing by a point here, okay, and that current will flow into the emitter. Clear? It will flow from VBB, it will flow from VBB, and it will flow like this. Leakage current will flow like this. Okay, right? So because of that, the current is negative. So I'm representing a small value here, okay, on the x-axis. Now what happens when we gradually, okay, now what happens when we gradually increase VE, right? The characteristics we get is like this. What is the reason? Now when we gradually increase VE, okay, right, then what happens? This reverse bias is reduced. Okay, when the reverse bias is reduced, obviously the current, right, the current also, the magnitude of the current reduces. So it is like this. Reverse bias, leakage current is flowing. When we gradually increase VE, okay, when we gradually increase VE, then what happens? At one point, it will change from reverse bias to forward bias. So the current will change from negative to positive, right? So when you gradually increase VE, the current will change from, initially when V is 0, the current is negative, it will change from negative to positive. So the characteristics will be like this, right? Then at one point, okay, at one point, and what is that point? See here. Now we are comparing VE, VA. Okay, we are comparing VE, VA. So far VE less than VA. Okay, but when VE becomes equal to VA, then what happens? Both the ends of the diode at the same potential, still the device is off. When the device turns on, when VE, okay, is greater than VA plus VD. What is VA plus VD? Right? VA is this voltage. VD is the cut-in voltage of the diode. Okay, right? So keeping that in point. So in simple words, when we gradually increase this particular VE, when we gradually increase this particular VE, current is changing from reverse saturation current to positive, right? Then when this V becomes sufficiently large, when this V becomes, we are now gradually increasing V, suppose. When this V becomes sufficiently large, okay, then the diode will turn on. P side voltage is increasing compared to N side is constant. So diode will turn on. When the diode turns on, okay, charge carriers are induced. Okay, when the diode is on, the current will flow like this, right? In this path, I hope all of you are able to see my mouse. So when the current flows like this, what is current? Flow of charge carriers. So charge carriers are now reaching in play in the region of RB1. Okay. So when charge carriers, see actually what happens, charge carriers are pushed from P side to N side. Now the charge carriers, okay, when V is gradually increased, charge carriers are pushed from P region to N region. Holes are pushed, but holes are positive charged. So they don't take this path. Okay, the holes, they don't take this path, rather the current flow will be like this, right? Okay, so now what happens because of that? Charge carriers are pushed towards RB1, okay, right? More the charge carriers, more the current, less the resistance. So RB1 will start to reduce, okay? RB1 will start to reduce. So when RB1 reduces, okay, when RB1 reduces, what happens as a result? The characteristics that we get, okay, will be like this. The emitter voltage will also reduce. Okay, the emitter voltage will also reduce because the emitter voltage, if you see this particular loop, the emitter voltage will be, okay, the diode voltage plus VA, right? So when RB1 reduces, VA reduces. When VA reduces, VE also reduces. So the characteristics will be like this, right? So what is happening between this point and here? Although the current is increasing, the voltage reduces. Thereafter, after certain point, what happens? When we keep on increasing the voltage, again the current will start to rise, and the characteristics will be like this, right? So what happens when we gradually change this VE? When we gradually change this VE, the current changes from reverse bias to forward bias. And when the current is forward bias, large number of charge carriers are injected into base region of RB1. So RB1 reduces means VA reduces. VE is nothing but the diode voltage plus VA. So VE also reduces until it reaches minimum. Thereafter, when you change this supply, again the VE rises. The characteristics will be like this. Very much similar to your tunnel diode. Okay, just see, very much similar to tunnel diode. The only difference is in tunnel diode, x-axis is voltage, y-axis is current. Here it is different. Okay, x-axis is current, y-axis is voltage. Shape of the characteristics is similar. Next, okay, of course there is a slight shift, but the shape of the characteristics is similar. Then what we do is we will name the region. Okay, first, this is peak point, valley point, same as tunnel diode. Peak point, valley point. So we will say peak current IP, then peak voltage VP. Okay. Next, this point is valley point. So valley current, valley voltage, same as tunnel. Okay, same as tunnel diode, right? Next, again, negative resistance region, same as tunnel diode. Okay. Negative resistance region, same as tunnel diode. Next, what is negative resistance region? Between peak point and valley point, same as, same as your tunnel diode. Between peak point and valley point, the region is negative resistance region. After valley point, it is saturation region. After valley point, you have saturation region. Okay. Next, to the left of peak point, right? What is the state of the device? The device is in cutoff because only leakage current is flowing. See here, the current is negligible, small current, although positive or negative, the current is small, negligible. So the device is in cutoff region. Okay. So we have taken We are considering two cases. What is the case when VE is less than VA? Next, when VE is greater than VA. Okay. So when VE is less than VA, the characteristics we get will be like this, right? Only from this point to peak point. When V is greater than VA, we get all this something like V shape. Okay, right? So that is when VE is greater than VA. And what is VE? Nothing but, okay, what is VE? Nothing but VE is nothing but PN junction diode voltage plus VA. Okay, so we can write VP as the PN junction diode voltage plus VA. Okay, you can write it as diode voltage plus VA. Okay. Next, what we will see is we will see the applications of this particular UJT. Okay, applications of the UJT. So first, see, any negative resistance is useful for two cases. One is oscillations, waveform generations. Let it be tunnel diode, okay? Let it be UJT. Negative resistance region has these two applications: oscillations, waveform generations. Okay, so because it has negative resistance, it is useful for these two applications. Then next application is it is useful in timing circuits. Both again, both your tunnel diode as well as UJT, it is useful in timing circuits. High speed switching is possible. Okay, what is the reason? It can easily jump from peak point to valley point. Okay, right? So it is useful in the timing circuit. Suppose as time goes on, say after 5 minutes you want to switch on something, okay, you can make use of this particular device. You have this timing in your, okay, washing machines, right? After 30 minutes automatically the machine turns off because the wash cycle is completed. For such applications you can use UJT. Okay, so applications of UJT, timing circuits. Next application is you can use it as a trigger to other devices. For example, if you want to turn on SCR or any other device, you can use UJT as a triggering device. Okay. Next application is it can be useful in automobile ignition circuits. Suppose, okay, how does your vehicle turns on? There is a small spark which is generated, okay, because of which your bike or your car is turning on. For such applications, you can use UJT. Next important application is Ujt relaxation oscillator. Okay, very simple circuit. Circuit is very simple. You know voltage divider bias circuit. Transistor, 4 resistances. Similar structure, but in place of 4 resistances, you have 3 resistance and then 1 capacitance. Okay, voltage divider bias 1, 2, 3, 4, 4 resistances. But in place of 4 resistances, 3 resistances are intact. In place of here, you have capacitor. So very simple circuit. And this is the symbol of UJT. Okay, this is the symbol of UJT. Same like FET, but the arrow is bent downwards. Same like JFET, which you have seen earlier. but the arrow is bent downward. That is the only difference in the symbol of, okay, UJT. So very simple structure. Let us label, okay, the resistances R1, R2. Next, these are the timing, okay, resistor, timing capacitor. So they are represented as RT and CT. Okay. Next, here we have three terminals. One terminal here, next terminal here, another terminal here. Three terminals of the transistor. These two we call them as the output terminals. V01 and then V02. Okay. And you know very well that this is base 1, the top is base 2, bottom is base 1, top is base 2, right? So what happens here? The capacitor charges, discharges, charges, discharges. Because of that, we get a